Okay. Okay, I hope you guys have all joined the quiz, alright? I haven't checked, so please wait, I think, for a few days. I believe I will check by tonight, and tomorrow or Wednesday I will give you the results. Okay. And probably I will just using email, using email and send to you. If you haven't give me your preferred email, I will just give you through the uh, university email. Okay, so just wait for a while. So meanwhile, this week I will focus on Laplace, okay, and I hope we can finish Laplace, okay, by this week. Uh, so today, this morning, afternoon, Wednesday morning, afternoon, I'm trying to finish uh, Laplace, at least until Dirac delta function. And Friday we will have midterm. Okay, we have midterm, and you can also check homework to help you to prepare your midterm. Uh, you don't need to write all the answers, okay, for the homework. I think you can just work half of half of it. It's okay. Okay. So in your homework, the next homework, you will see some sections from exercises like 2.4, 2.5, 3.3, blah blah blah, right? What you are going to do is each sections at least working 2 or 3 questions. That's okay, half of it, and you can send me your homework. Okay, not send, just upload your homework on the drive folder. Upload your homework. You can decide which part you are working. Okay. And yeah, no need to work all questions. I think it probably too much for if you work all homework. So just work 50%. I think okay. Okay. So last sections we discussed the inverse, right? Laplace inverse. But before we continue, let me just make some emphasis uh, of this uniqueness, okay, of this uniqueness exponential order. Okay. What do I mean with this existence uh, exponential orders? Okay. Let me give you some some illustrations. Okay, so if we take uh, okay, so if we take that all this graph, okay, the blue color is basically saying that it's uh, at least it's is below the red one, the e with power of t, which means that if we have for c positive, okay, for c positive, if we have any t with power of n, it's always less equal than our um, analytical function of the exponent m e ct, or we can write in terms of t with power of n divided by e ct with absolute value to make sure that this is positive. This is always less than m for t greater than t. Okay, now if you look at the left side, the picture here, this is what we are having. So a, if we look at, this is just a linear functions, is t, let's say t. Okay, we can say that this is less equal e to the t, right? Okay, this is, of course, it's our inequality. It's fit with this picture. And then the second curve, we have e with power of negative t, it's always less equal e with power of t, right? And for the cosine here, if we look at this, always less equal than 2e power of t, right? Okay, so which means that all these three, the blue graph, we can say the blue graph are of exponential order, okay? Because we have this always less equal m, some constant multiplied with e with power of ct. But if we are going to look another examples, okay? If we have, for example, we have a function that is e with power of t squared, okay? If we are going to use our inequality, then we can say for some ct like that, we have a ratio that this will going to be t squared minus ct, or this is going to be t minus c. And if we look at this, okay, if we look at this, for any value of c, okay, for any value of c, this will going to be approaching infinity as we increase our t to infinity. So if you increase your t for any value, okay, because it's in the power of exponent, it will increase, and you will see that it's unstoppable. Okay? It will always increase until infinity. And you can also check by reasoning using the e with power of negative st multiplied with e. Let's say this is the functions, right? We can also say that this is going to be infinity as, or maybe for any s, okay, for any s, and the improper integral, which we define as a Laplace e, if we try to find, this will result in diverge. And by diverge, we can conclude that the Laplace of e with power of t squared doesn't exist. Okay. So if we again we look at for what is happening here, we are going to see that the et square here, it's crossing this, right? It's crossing the e with power of ct, which means that our inequality here is not less equal. It's not less equal some constant, okay, because it is the line, right? Okay, so see the graphs, it's not exponential, okay. Or we can just say we can say to make it much more sense, we can say that e with power of t squared is grows faster than any positive linear power of e for, let's say, t greater than c greater than 0. Okay, and then If you want to observe analytically, you can observe using the improper integral, or you can see this ratio. Okay, in this ratio, and imagine if you increase t, what is happening with the ratio. Okay. Okay, this is just an additional information to help you get more idea of what is uh, the existence. Okay, when you are doing Laplace. Okay, what kind of functions you can put in for a Laplace. Okay, okay, that's just additional information, and of course we also have learned that uh, if we have piecewise, okay, piecewise definition like this, piecewise continuous functions, we can also try to check the Laplace. Okay? We can try to check the Laplace, and of course, by doing so, in our calculation in the integration, we are going to separate the point that is discrete or discontinuous, okay? Which is the discontinuity is happening at, I think here is happening at 3, right? At t equal 3, it's supposed to be having some sort of discrete, and we separate becomes two separate integral, and we can have uh, an idea what is happening by looking at the functions. Okay, the function itself is getting 0, so this whole thing is getting 0, and the rest is we just having this 3 to infinity, right? So we have uh, positive, okay, positive of this component. Okay, this type of function, space-wise type of function, I think it will be very important. Okay. I think we will discuss more in. I think if we have time, maybe this morning or maybe next afternoon class, okay, we will have more discussions about this type of function we call unit step functions. Okay, with that will be later. Okay, so that's the existence, uniqueness, and then inverse transform. We already doing some over here, right? The inverse. So why we need the inverse of Laplace? Because if we want to solve some sort of functions that the differential equations, we are going to use both Laplace and its inverse, okay, to for finding its solution. Later we will discuss about that, okay. But at least you learn how to do the inverse, okay, how to do the inverse. Basically, you need to do some after you have the Laplace transformations, then we can revert back that transformations back to the original equation. So whenever you have usually function of s, okay, and you have a fraction like this, you can imagine and think what kind of functions that we can revert back this function of s into function of t. Okay, and some of the works that probably we are going to see is using partial fractions, and I hope, okay, I hope you guys can have more review on the partial fractions. Okay, we were going to see more if we have uh, time for some example, but let me continue for the transform of derivative of our functions. So let me check which one we have. Okay. Okay, so partial fraction, if you have any maybe not really know what to do, I suggest you to review uh, some of calculus problems, especially the technique of integrations, and you can see some sections which we call the partial fraction. So you can try to read that out. And why partial fraction is important, because it can separate your big rational function become a very small fraction, and you can integrate each fractions easily rather than the bulky one, right? So basically here we can say we can separate this big bulky complicated fractions becomes small fractions, and basically by Laplace we say that we are going to integrate, right? We are going to integrate, so we can integrate easily each sections, each fractions. Okay. If we have, for example, if you remember, in partial fraction we also have we call the so if we have let's just focus on the denominator. Okay. So we have, if we have s minus 1 squared, s plus, let's say s plus 2. Okay. This we can say we can have a repeated factor, so we can write s minus 1 plus s minus 1 but square plus s plus 2, and we can just write a b c, just a single constant. Okay, that's the idea of partial fraction, in which we are having repeated factors. Okay? Or if you have s cubed like this, what will happen? We are having s squared, s cubed, and then plus the last one is s plus 2. This we call repeated linear factors. Okay, I hope still remember. Okay, I'm just giving you some hint. If we have time, we can discuss more. Okay, but let me continue for the next sections, which is the transform of derivatives. So if we have, let's say we have f of t, and we want to Laplace this, we can, right? We already doing that. Okay. But if we are having the same function, but we are going to look at its derivative. So for example, the f prime t. Okay. So the first thing, if you want to prove the Laplace, we can just take integral, right? The improper integral. Take the definitions of Laplace. And put the functions on the right side. Okay. And what we are going to do, we are going to do some integration by parts. Okay, integration by parts. What I want to do here is I will integrate the f prime and it become ft, and I will differentiate this and making sorry. Okay, now we are having plus minus, so we will have e negative s t f t from 0 to infinity. Minus become plus s e negative s t f t dt. Okay, if we take this, what will happen? The infinity one becomes 0. The rest is just negative f0, right? Or we can, if you want to write clearly, this is 0 in the front like that. But we can just ignore 0. And the second integration here, we have 0 infinity plus, let me factor out s, and we are going to see, okay, now we can say the right side, this is the Laplace, right? This is the Laplace of f of t, right? So we can say that this is minus f of 0 plus s, okay, multiply with Laplace of f of t. Or we can say as we can change this Laplace f of t becomes f big capital F after transformation minus f0. Okay, so we can say that this is our Laplace transform of derivatives. Okay. Okay. And then, okay, if we have this first derivative, we can try also for the second derivative. Okay, the second derivative. And of course, this f, okay, to make it clear, we can always say that this f is differentiable function to make so that we can differentiate this differentiable functions of exponential order, that is f of t is less equal m e with power of ct for some constant m and c. And we can say that the Laplace of f of t exists. And limit as t increasing or going to be infinity of this this is equal 0 when s is greater than c. Okay. Okay. Now, if we look for another derivative, okay, so if we have first derivative, if we increase the order, okay, like second derivatives, the third derivatives, what will happen? Okay. So let's just check. Okay, let's just check. Okay. So let's say we have f double prime t. So it's the same usual improper integral, and we are having this f double prime t dt. Now, same thing, we are going to use integration by part, and I will just integrate the f double prime to make it f prime. And you will see that we will have some sort of pattern. So we will have e to the power of negative st f prime t. Okay. And then we have plus, let me just write and factor out s, and then integration 0 to infinity of e negative st f prime t dt. Okay. Again, this part here, this will gives the Laplace, right? So we can say that this is Laplace of f prime t. Okay. Now this part will be a 0 minus f prime 0. Okay. So what will happen here is we are going to have, or if we remember the Laplace of f prime t from the previous section, this will give the, or let me write here, this will give s f s minus f0, like that. So all in all, this will give, the transformation will give this is, let me write here, s multiplied with this. Okay, so we will have s squared, capital F s, minus s f 0 minus f prime 0. Okay, now let's try another one. Let's try the third derivatives. Okay, and again, same thing, we are having the e, this integration, this derivative. So for the part e, we will also always have the same structure, right? The difference is just the derivatives part. Okay, so this will be giving us e f double prime t. This is plus s, factoring out the s, and then f double prime t dt. We can say that this is the Laplace of f double prime. So f double prime is s squared f s minus s f0 minus f prime 0, right? That's a double prime. So we will have s multiply with the whole thing here. Okay, and then we can write down, this will give you negative, or let me write here, this will give you a negative f double prime 0 now. So we will have, let me write the s cubed for the first terms, s cubed capital F s minus s squared f0 minus s f prime 0 minus f double prime 0. This is for Laplace of the third derivatives. And if you're doing more and more using 4, 5, 6, and 7, you'll get somewhat similar patterns. And then we can just look at the patterns. Okay, let me give you the patterns here. Let me give you from the first derivatives. Okay. Or let me give you the final result. S f fs minus f0 f double prime. This will be s squared fs minus f f0 minus f prime 0. And you will notice that if I have the third derivative, this will give you s cubed. Okay. Now s squared, and then s, okay, and then f double prime. And you can predict, what will happen if we increase the derivative with 4, 5, 6? Okay, so if we increase, let's say we have 4. Usually 4 is writing like this. So whenever you have power but have bracket, which means it's derivative, okay, we need to take derivative 4 times. So we are having as 4 minus s cubed minus s squared minus s, right? F0, oh, sorry. Why f? It should be f prime. This is f double prime. Uh, 3, 1, 2 minus f. Yeah, 3. Okay. Now if we have 5, for example 5, we can increase again and write with similar pattern as 5, as 4, this is as cubed, this is as squared, this is as, sorry, this is 3, and then f with 4 derivative 0. Okay, so you can have patterns for this Laplace transform for derivatives. Okay, now what the important here is, you know the pattern, you can at least know why we have this pattern. That's the most important thing. Okay? And you can write off any derivative if you want to Laplace. You know what the pattern is. Okay, that's the important thing. What I want to write here is, like, we can write in the general forms the theorem of this transform of derivatives. If you want to take notes, I think you can take notes this part here, the structure, how we can write the so if we have the transform of derivatives, you will notice that it will reflect your derivatives for each s. Okay? So if you have the first derivative, you have 1s. You have the second derivative, you have s squared and s. Okay? You have some sort of like a quadratic, right? If you have the third derivative, you have the cubic, right? Cubic. And by doing this, what's the idea behind all this? What's the purpose? Well, now you know you can transform any derivative with Laplace and then make it into algebraic. Okay, you can make it into linear, quadratic, cubic, polynomial formula, right? You can have polynomial here, polynomial of s, right? Okay. Okay, let me write the theorem. So if, okay, we have f, f prime, f double prime, until f n minus 1. They are all continuous on from 0 to infinity. Okay, this is the domain of Laplace. Okay, and are of exponent. Let me write exponent with cream. Exponential order, as we proved previously. And if f power of n of t is piecewise continuous on the interval, then we can say the Laplace will be having the we can write s to the power of n, as we mentioned before, plus Sn minus 1 of f0 minus Sn minus 2 f prime 0 minus dot 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 until minus Fn minus 1 0. Okay, so if we look here and we see that it fit with our example, right? So we say that the where f of s is Laplace of f of t. Okay. Okay, as I mentioned before, what we are going to use Laplace for is to transform differential equations into algebraic one, right? So Laplace transform, let me write here the big idea. Okay, Laplace transform of linear differential equations with constant coefficient becomes an algebraic equations. Algebraic equations, let me write just with capital Y like that. So if we have let's say an Laplace Laplace of d squared y dt n plus a n minus 1 Laplace of d n minus 1 y dt n minus 1 plus dot 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 plus a0 Laplace of y Laplace of, let's say we have function of g on the right side. Now from this theorem we will get this an multiply with the Laplace. The Laplace become s with power of n y s minus s n minus 1 y 0 minus s sy n minus 1. This is the derivative, right, of 0. And then this is the first part here. This becomes this. I think we can just make it very small. And then plus a n minus 1. This will be s n minus 1 of y, capital Y s, minus s n minus 2 y 0 minus until the derivative n minus 1 or r minus 2, sorry, of 0. This will be this. Okay, and then plus dot 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 plus a0 Laplace of y becomes just y s, and Laplace of g becomes g of s. Okay, well, please do not mind if you see any complicated like Sn minus 1, usually we have problem when we see this, and we might we seems not really sure what's happening. But if we going back to what will happen, okay, as long as you know the structure, for what's happening in first derivative, second derivative, third derivative, and other higher derivatives, if you know the structure, you can definitely transform the using Laplace any differential equation which is linear, you can transform into algebraic equation. Okay. Let me give you some steps. Okay, some steps. Let me give you an example first. Okay, example. We can take example and then maybe write some procedure. Okay, what the first thing you need to do, and then what will happen. At least 3 or 4 steps. Okay, that you are going to solve using this Laplace. Uh, Using Laplace means you are going to transform differential equations. And after you transform into algebraic, maybe you can solve this algebraic, you can simplify, and then transform back with inverse. So you inverse, and then you are going back to the original, having some variables from original equations, and then write the solutions, okay, the y. Usually y equals something. Okay, let me give you the example. Or maybe do you have any questions first? Do you have any questions first? I think I can go for an example. Laplace uh, seem complicated, but if you see the patterns, if you see the structures, you will, at least if you know how the pattern will be, it will be not too difficult, not too difficult. Okay. Okay. Let me give you an example. We have dy over dt plus 3y equal 13 sine 2t, and we have the initial value of y0 equals 6. Now, from the previous differential equation, higher order, or just the linear one, we know that we can solve this, right, using undetermined coefficients. You can use any method you are going to use. Okay. You can find the homogeneous one. You can find, and then plus the particular solutions, right? Complementary solution, particular solution. But let me just rephrase this with the Laplace. Okay. So using Laplace means we are going to transform all these components. So first step, Laplace transform our differential equation, our dE. Okay. So take Laplace. Three Laplace and then 13 Laplace of sine. Okay. We know that from the previous, let me just write so that you are familiar. If we have dy or dt, this is the first derivative, right? So we will have as capital Y as, okay, and then minus y0, okay. And y0, we have the initial value of when x0 is when t0, y is equal 6. So we can write as capital S minus 6. Okay. And remember, oh, this is supposed to be y. Sorry. The sign, if we remember our table before the Laplace, the sign is 2 over s squared plus 4, right? S squared plus beta. Remember that we have the sign beta t. This is beta divided by s squared plus beta squared. Okay, for sine. For cos, if you remember, this is s squared plus beta squared. The similar thing is the denominator, right? Okay. Now we are having the we are going to have s capital Y s minus 6 plus 3. This will becomes y s like that, and then equal 2 multiplied by 13 is 26 divided by s squared plus 4. So what will happen here? What will happen next? Let's just try to rearrange and try to simplify, okay? And then maybe we can at least solve first with respect to the capital Y. Okay, so second step, rearrange the uh, the Laplace result. Okay, so let's rearrange. We can say that as, or we can write s plus 3, right? And then we move 6 to the right side. So 6 plus 26 over s squared plus 4. Okay. And then we divide all with s plus 3. So 6 s plus 3 plus 26 s plus 3 s squared plus 4. Okay. Now what will happen? We're going to have or if we want to combine these two, we can do this as well. This will be s plus 3 s squared plus 4, and then we solve this s squared plus 4 multiplied by 6. This will be 6s squared, right? 6s squared plus 24, 24, 26, 50, right? Okay, we can write like that. Now we have this, at least this as our ys. Okay. Now I think we can do some partial fractions. So third step, maybe rearrange further if we have, probably using partial fractions. Frequently we are going to use this partial fraction. So 6s squared plus 50 okay, this will be going to have s plus 3 plus s squared plus 4 is, the discriminant is I think less 0, right? You could see that this will be going to be a complex, but since in the partial fractions we not really care much about this complex or not, so we can just write the s squared plus 4, but the top equations will be bx plus c. Okay. Okay, we can take some times to solve, so that we take this equation. Okay. So we can take a s squared plus 4 plus bx plus c s plus 3, and this is equal to 6 s squared plus 50. Oh, it's not x, sorry. It should be s, the variable. Okay. So using the variable s, sorry. So we can have as squared plus 4a plus bs squared plus cs plus 3bs plus 3c. Okay, so we can grouping the same variable, and then uh, c plus 3b as, right? Plus 4a plus 3c. So a plus b is 6, c plus 3b is 0, and 4a plus 3c is 50. Okay. Okay, we can have this is multiplied by 3, and then we can subtract. So 3a minus c is 6. So same way we can multiply by 3. So 9a minus 3c equal 18. This will be give you 13a is 68. So a is what? 3c, 3a minus c. Okay, let me check. Oh, this is supposed to be 18 here. Sorry. 3a. Okay. So this is not this. So 18 by 3 is 54. So 104 is 13a. So a is okay, 8. A is 8. A is 8 and b is negative 8, right? Oh, no, not 8. So a is 8, b is negative 2, right? 6 minus 8 is negative 2. And c uh, minus 6b is 0. So c plus, let me write one by one. So c is 6. Okay. So we will have 8s plus 3. Let me just write plus, and then this is minus 2s plus 6, or 6 minus 2s s squared plus 4. Okay. Well, anyway, I just realized that I think we can just make s equal negative 3, and then put here will be 0, right? The whole thing here will be 0. This thing here will be 13. This thing here will be 9, 54, 50, 104, and you get the same 13a equal 104, right? I think it will be very very helpful, right? And when you get the a, you will get also the other part as well. Maybe we can take uh, b with equal to something here. Okay, that's another way to look at it. But let's just say we are having this as our partial fractions. Okay, now what's next? What's the step we are going to do? So we already have this as our partial fractions result. So the next thing is the what's let me third step. Okay, the fourth step, we are going to take the inverse Laplace. So you write that our capital YS is 8. Okay. Now dy of t, this will be 8 Laplace inverse of 1 over s plus 3 plus, or maybe take minus first for 2s, so 2 Laplace inverse of s over s squared plus 4, and then plus 6 Laplace Laplace inverse of 1 over, or to make it clear, let me write this is 3 and this is 2. Okay, why? Because of the structure. You will see later. Okay, now remember, 1 over s plus 3, we will have 8e negative 3t, right? Remember the Laplace, the inverse one. And then minus 2 Laplace inverse of s over s squared plus 4 is cosine 2t, right? And this plus 3 Laplace inverse of this is sine 2t. So the solution using the Laplace, we are getting this y of t equal 8 exponent with power of negative 3t minus 2 cosine 2t plus 3 sine 2t. That will be our solution. Okay. So basically, if we summarize what we have done here, so we need to find the results. Okay, we need to find our yt that satisfies differential equation and initial conditions, right? Okay, and then apply Laplace. Laplace. Okay. And then dE become algebraic equations, right? And then we solve first. Solve algebraic for capital YS. Okay. And then what's happened after we solve the algebraic one, we apply the Laplace inverse. Laplace inverse. And then we say we are going to have the solution y of t for original initial value problem. Okay, so the steps: see the differential equation, transform it into with Laplace, solve for the capital YS, transform back using Laplace inverse. Okay, is that clear? Okay, is it clear? Okay, is it clear for you? Okay, maybe any question first? Questions? Okay, any questions? Well, it doesn't need to be capital Y. This is just for Y, it's capital Y. If you have just F, capital F. Okay, if you have X, you have capital X. It depends on what kind of function you have, what kind of variable you have. You can just look at the pattern, and all will be using the same structure and pattern. Okay. Okay, well, we are looking at this. Let me just wait for a few minutes. Okay. Okay, any question? Any question? No. I think let me just give you another example. Okay, another example to see uh, where we can apply this for any results. For any variable, any results, as long as it is using the same constructions with this Laplace, all the same, its existence, uniqueness. Okay, so we can apply for all variables. Okay, let me give you an example. Let's say we have function x with respect to variable t. Okay, let's say we have uh, x double prime t plus xt equal cosine 2t. And we have a conditions that is, and the other one is this. Okay, let me give you a few minutes, okay, a couple of minutes, 1 minute, 2 minutes to check whether you are able to transform this with Laplace and then transform back with its inverse and find the solution. Okay, so the question is just find solution xt for given de. Okay, let me give you a couple of minutes. Okay. Uh, okay, let's solve it together. We take the Laplace. Okay, we take the Laplace. First, we take the Laplace. We can write. Let me write here. Okay, take Laplace. Okay, take Laplace. Laplace of x double prime t. Okay, plus Laplace of xt plus of cosine 2t. Well, the beautiful thing with Laplace is we are getting the algebraic equation, right? We have the, for this x double prime, remember we have s squared, right? And then become the capital X to differentiate the transformation, that this is x s like that, minus s, right? And then write the small x, and then minus x prime 0. And that's for the x double prime. Now xt is just give you big X of s. And then cosine is s divided with s squared plus 4. Okay, again. So we take Laplace. So take Laplace and rearrange. Rearrange. We take the we take the we try to solve the capital X. Okay, now capital X. So let me just write s squared x. Sorry. And plus x. Okay. And the initial conditions, this is 1, so minus 1. And then the second conditions that this will be 0, right? This is 0, this is 1. Okay. Okay, now we can rearrange. This is capital X. This is s squared plus 1. And I will move 1 to the right side. So s squared plus 4 plus 1. Okay. Okay, this will be equal to, we divide by s squared plus 1. Okay. Well, we can take some time to make it our partial fractions. Okay. This is s. This is plus s squared plus 4. S squared plus 4. Or maybe let me just write with more beautiful s. Okay. Okay, take some time to use partial fractions. Partial fractions. So partial fraction becomes commonly used for rearrangement. Mostly we are using this. Okay, so we have s squared plus 4 plus s squared plus 1. And this will be a s plus b, c s plus d. As plus b multiplied with s squared plus 1 plus cs plus d multiplied with s squared plus 4. This is equal to s squared plus s plus 4. Okay. Um, oh, I think, wait, before we solve this, we can just solve this, the half part of it. So partial fractions, maybe here. So just partial fraction this one. I think this will be easier. Okay? And then leave this part, just write 1 s squared plus 1 like that. And we try to solve this. Okay. Now as plus b s squared plus 1 plus cs plus d s squared plus 4. Okay. Let's solve this. For d. Okay. So the key here, I believe, is your skill in doing these partial fractions becomes somewhat important. This is equal to just s. So one by one, we check that this is 0. B plus D is also 0. A plus 4C is equal 1. And B plus 4D is 0. Okay. Now C is minus A. A is minus 1 over 3. C is 1 over 3. And this one doesn't matter, it's just 0. So we are just taking this A and C. So this will be, let me write the positive at the first one, the C. So we have 1 over 3 s squared plus 1 minus 1 over 3 s squared plus 4 plus 1 over s squared plus 1. Okay. Now this is our, or let me write with capital X the solutions. Okay. Now this will be 1 over 3 s over s squared plus 1 is cosine, right? Cosine t. Minus 1 over 3. So this will be inverse Laplace. Inverse Laplace, doing the Laplace inverse. Or let me write Laplace inverse of capital X, like that. S over x squared plus 4 is cosine 2t. 1 over x squared plus 1 is sine, right? Sine t. Or we can say that the xt, the small x, the solutions for the differential equations is equal to 1 over 3 cos t minus cos 2t plus sine t. Okay. Okay, I hope it's clear now. So yeah, the partial fractions part uh, will be very important. Okay, so maybe giving you another example, and then we can move to the next section. Okay, now this is another example. Okay, giving you next example. Let me give you solve y double prime minus 3y prime plus 2y equal e with power of negative 4. I'll try this one. Oh, let me give you initial conditions to make it clear. Okay, so that you can compute the algebra. Well, of course, in differential equations, if you have this, then probably you can use not any method in differential equations, right? Right. I think you can solve this easily using using any method that you have learned before. But in our case, in the Laplace, you need to use the Laplace transform, and you need to show clearly each part, each step. When you do Laplace, rearrange the transformations, and then doing the inverse of Laplace and find the solution. Okay. So take Laplace. Okay, take Laplace. So Laplace of y double prime minus 3 Laplace of y prime plus 2 Laplace of y, and then Laplace of e with power of negative 4t. Okay. So Laplace of y double prime is s squared capital Y s minus s and minus y prime, and minus 3 s y capital y capital S, and then minus y0, and then plus 2 y capital Y s equal 1 over s minus alpha. Alpha is negative 4, so s plus 4. Okay. Now looking here, we have y0 is 1, y prime 0 is 5. So we can complete this by taking the ys and factor ys, s squared minus 3s, right? And then plus 2. And then negative s, right? Negative s, negative 5, negative 6. Y prime 0, negative 5, negative 1. Oh, I think I need to be clarify this. Let me write negative 3. This is supposed to be having this to make it clear. So negative 3, so plus 3. 3 minus 5 is minus 2. So minus 2. So minus 2 is equal 1 over s plus 4. So s plus 2 plus 1 over s plus 4 divide by 1 over s squared plus minus 3s plus 2. Okay. Okay, so s plus 2 divided by plus 1 s plus 4 s squared minus 3s plus 2. Okay. Okay, now we have this. I think we can just combine to make it clear. I think we can factor out this s minus 1, s minus 2, right? So s plus 4, s minus 1, s minus 2, s plus 2, s plus 4, s plus 2, s plus 4. So s squared plus 6x, s squared plus 6s plus 8 plus 1 plus 9, right? Okay. And again, we are having the compositions using partial fractions. Okay. So s squared minus 3s plus 2 multiplied with a plus s squared plus 2s minus 8. It's b. Or let me write seemingly to just using s minus 1, s minus 2. So let s equal 1. So this will be 0. And this will be 5, negative 1. So negative 5b. This will be 0. So this will be 1 plus 6, 7 plus 9, 16. I think we have done this before, right? Let me clearly check. Yeah, this one. Okay, so looking at this, okay, we are having the same similar. But let me just make sure that this is correct. So we let s equal to, this is 0, 0, 6, 6c, 4 plus 12, 16 is 25. So c is 6. And let s equal negative 4. 0, 0, negative 4, negative 1, negative 5, negative 5, negative 6, 30a. 16, 25, negative 24 is 1. So a is 1 over 30. So 1 over 30, 1 over s plus 4 plus or minus and do the Laplace inverse. E negative 4t minus, this is e negative t plus e 2t. Oh, this is t, sorry. Okay, this is the results. The same results, right? The same results. Okay. Another property that still important. Another property, the property of capital F as S going to be infinity. So if F is a piecewise function or piecewise continuous function on the domain of the Laplace and of exponential order, then limit as S going to be infinity of Laplace of functions of t, ft, this will be resulting theorem. Okay, so ft is piecewise continuous on piecewise continuous on closed interval 0 to t. Let's say t, or let me write. Okay, it's necessarily bounded to this interval. That is, interval is less than m1, which is equal to this. So because f also exponential order, so there exists a constant gamma that is, we call the m2, that is positive, and capital T is also positive, such that the absolute value of f is less equal of m to e with power of gamma t. So gamma is a constant to multiply the order in the exponential. So this is for t is greater than the capital T. So if m denotes maximum of m1 and m2, and c denotes the maximum of, let me write a little bit right to the left. This is maximum of 0 to gamma. Okay. So what will happen? That is our Laplace of functions t absolute value. This will be equal to and this will be having less than our constant m. Multiply with e negative st, multiply with e ct. So it's always less than this part. That is equal negative m. After we solve this integrations, e, and then we can add the exponent, and s minus c, we integrate from 0 to infinity, and we are having m s minus c. For s greater than c. So as a consequence, so as getting infinity, we will have that the Laplace of f of t, this will be getting 0. So Laplace of f of t will be 0 as going. Okay. Okay. This is just is to denote that when s is going to be infinity for f of s, then if the f is piecewise continuous and exponential order, then the limit of the Laplace function of t as s going to be infinite, the Laplace will be 0. The Laplace will be 0. Okay, this property. The below here is just a proving parts. Well, if you really not to understand this part, just looking at this one, the top one. Okay. Okay. So Laplace definitions, finish, inverse, and also the transform of derivatives and how to solve using Laplace. We already done. The next part is first we will go to the translation theorem. Okay? So Laplace, aside from we can transform Laplace, we can also imagine the Laplace being shifted. Okay? Being shifted to the right, to the left. Okay? We can translate uh, the graph. Okay? And when we translate the graph, we simply shifted the variables, right? The variables. Okay. Let me go through next page. Okay, if you have any questions, you can also write in the chat box. Okay. So translation theorem. Let me just give you the idea. Okay. Now remember, okay, when we shifted the graphs to the right side, what we are going to do is we are going to shift it the variable s in this part, right? Remember, when you have a graph, you can shift the graph through the vertical axis or horizontal axis, right? If you want to shift it to the vertical axis, if you want to going up, you need to plus, right? You need to plus the function with the constant, right? Like you move 3 units up, then you need to plus 3, right? If you're going down, you need to minus, right? But if you want to go to the right side and the left side within this horizontal axis, if you want to go to the right, then the functions become, if the function, if f of x, then if you want to go to the right 2 units, then you will go f, and the function become x minus, right? X minus a constant, like x minus 2 or x minus any constant that you want to move. Right? If you want to go to the left, you need to plus the x, right? Okay. Okay, I hope you still remember that. Now we have this. We shifted this f of s to the right. So we are going to have s minus the constant. The constant here is a positive constant that is greater than 0. Okay. And then this part is a, s equal a, right? Okay. And then you can move on. Okay. So the first theorem here is this, we call this also shifting theorem or translation theorem. So if the Laplace is of f of t equal the capital F, like that, and a is any real number, okay, then the Laplace of e with power of a t f of t, this is equal to f s minus a. Let me write this theorem first, and then we can have some discussion. And we can prove this expression by taking the Laplace integrations. And we can take the integral. So let me write here the integral, or maybe here. So the integral, if you remember, that if we have e with power of atf of t, this is basically saying that we are integrate from 0 to infinity that is our integral. Okay, we can combine this exponent. Okay, right? And then we have f of t dt. And it's immediately we saw that this we say equal to f s minus a, right? So if we consider the s is real variable, then this graph we can see that this is shifted to the right with some a unit, Sometimes we can also write the translations with terms, let's say this is at, ft, like that. We can write this, right here. This is equal to the Laplace of f of t, but with s transform or shifted to s minus a. We can write also some terms, okay, like this terms. What this transformation means is whenever you have some exponent e functions like this, and you have another functions, you can write this by using you can Laplace the function first and then shift it the s. Okay, so how do we do this is, for example, if we have Laplace of e with power of 5t, function is t cubed. For example, that is our Laplace. We say that we are going to Laplace our t cubed, and then we are going to shift it our s to s minus 5. Okay, or if we want to going to be more clear what's happening here, the t cubed Laplace becomes 3 factorial divided by s with power of 4, and then we still write this is s shifted to s minus 5, or this will be 3 factorial becomes 6, and the s we are going to change with s minus 5 with power of 4. Okay, so it makes the simplicity, if you have the e with power of something t multiply with some functions that you already know the Laplace, we can simply just taking the Laplace of that functions and then shift it through the power of the e. Okay, let's try another one. So if you have a Laplace of e with power of negative 2t, let's say cosine 4t. This is simply we say that this is a Laplace, okay, of cos t or cos 4t, and then shift it s to s minus minus 2, so s plus 2. Okay, now cos 4t, we know that this is s divided by s squared plus beta squared. Beta is 4, so it's 16, and then shift it s to s plus 2. So we are going to have s becomes s plus 2 like that, and then over we are having s plus 2 squared plus 16. Okay, Okay, so at least in your minds, if we are getting this new translation, we are going to also, if we reverse, we are going to need something, right? But I think that will be in the next section. But let me just say, uh, in this case, we can also have the inverse of the shifted one. So the inverse of f s minus a. Okay, that will be the next page. Okay, next page. But I want you to just to look first. Okay, what will happen? So I believe this is really important steps. Okay, in our Laplace. So whenever you have a function, not a function, whenever you have equations that is going to have a component of exponent in some parts, and then also the other part is a component that you know the Laplace of, then you can think, if you combine those together, what the Laplace of it. Okay, any questions first? Any questions? Okay, is it clear for Laplace? Using Laplace for solving dE, the differential equation, and now we have the shifted Laplace. Any questions? No? And still, for some problem, the partial fractions is becoming more and more frequent. So I hope if you still have difficulty in the partial fractions, please review by yourself. Okay, what is partial fractions, how to use it. Okay, basically partial fractions, we need to separate, becomes each small fraction. We take the compositions of a big fraction into small fractions. That's the partial fraction. Okay, let me go to the new page. So the inverse is, if you have Laplace inverse of the f s minus a, okay, this will be Laplace. Sorry, it's not curvy enough. So Laplace inverse of the f of s, and then this will be s going to be s minus a. This is equal to e at f t, where ft is Laplace inverse of capital F x. So whenever you have the structure in your equations, you have maybe s plus something, s minus something, and then squared. Probably you can take that as maybe there is translation happening, and you can convert within the translations. Okay. I think we can give you an example here. So Laplace inverse of 2s plus 5 over s minus 3 squared. Okay, now as I mentioned, if we need to partial fraction this to decompose the fractions, we will see the repeated linear factors. Okay, this is we call the repeated linear factors in the partial fraction. So we can analyze the fractions first before we use a Laplace to invert the Laplace inverse to find the solution. We can say that this is practically, we can decompose becomes two separate structure, and then we have a constant A, constant B. Okay, use the partial fraction. Okay. Now we have A s minus 3 plus B. Okay, and this is equal. Okay, I think this is simple linear system, so we can solve this thing. So A is 2, and negative 3A plus B is 5. So negative 6 plus B is 5, so B is 11. So we can input the constant. Okay, we can input like that. So we can input the first one become the Laplace inverse of 1 over s minus 3. We can get this easily. And the second one, we have the Laplace inverse 11 Laplace inverse of 1 over s minus 3 squared. I think we can take this to the right, to the left, and make it a little bit smaller. Okay, now the problem is this one, right? So let me just write. This is Laplace inverse of 1 over s minus 3 squared. So what will happen here? This is, we say this is Laplace inverse of 1 over s squared, where the s is changing to s minus 3, right? We can say. Or we say that this is precisely e with power of 3t t. Okay? So 1 over s squared is, so 1 over s squared is t, right? So this translations goes to this e with power of, this is the translations. Okay. Okay, so we can write that Laplace inverse of 2x plus 5 divided by s minus 3 squared. This is 2 Laplace inverse of 1 over s minus 3 is e with power of 3t plus 11, and then this will be e 3t t. Okay, so this is the result. Okay, so I hope translations now also can be added to your Laplacian knowledge. Okay. Okay, now the first part here, we are mostly using the partial fractions to see the form. Right? The next example, try to find Laplace inverse of s over 2. Well, let me write using more clear, s over 2. So this is not 5, this is s, okay, plus 5 over 3. and this is s squared plus 4s plus 6. Okay. Now what will happen here, okay, what will happen here is another way to look at this Laplace inverse is what we are going to do to solve this. Is there any way that we are having a clear picture of uh, what this fraction has? Okay? One idea that probably can help is if we can say complete the square, okay, of this quadratic, and see when we with this, if this completed square can have some simplification. Okay, so first look at this fractions. So look at this s squared plus 4s plus 6. If you want to complete the square, you need to have plus 4, right? And then plus 6 minus 4, right? So you need to have s plus 2 squared plus 2, right? That's the equation that you want, okay, if you want to complete the square. So let's just try and write those at here. Let's write here s plus 2 squared plus 2. And then let's try to maybe takes 1/2 outside of this s over 2. If you take 1/2, so the question is, maybe let's think on from here. We take that the bottom one here having the s plus 2. So can we make s plus 2 on the top equation, so that we can see that these two have s plus 2. So let's just write s plus 2. We need to multiply with half to make it s over 2. We are having plus 1, right? Plus 1. So we need to plus to make it 5 over 3. We need to have 2 over 3, right? So plus 2 over 3. Okay? So we can separate this. The first equation we have 1 over 2 s plus 2 divided by s plus 2 squared plus 2. And the second one is plus 2 over 3, 1 over. Okay, we have these two equations. Okay, I think we can take the Laplace inverse as mentioned in the question there. So Laplace inverse, let me write here. Laplace inverse of s squared plus 4s plus 6 is half Laplace inverse of s plus 2 and then plus 2 over 3 Laplace inverse 1 over, sorry, s plus 2 squared plus 2. Okay. Now looking at here, we know that this s plus 2 has the same. So remember what kind of Laplace that is. We are having s squared plus 2. Remember that, right? So this is, we can write that this is Laplace inverse of s over s plus 2. And then we say that this is shifted from s to s minus 2. Or s plus 2, sorry. And this part here, because we see that this is having only a constant, and it has the similar s squared plus beta squared, right? So if we have this is beta here, then we need to multiply with, or we need to divide beta here, right? So we can say that because it's 2, so we need to have a square root of 2. So 2 over 3 square root of 2. And we can say this is Laplace inverse of square root of 2 divided by s squared plus 2. This is from s to s plus 2 shifted. Okay. Now we can write half. Okay. Now the shifted one having e with power of it's s plus 2. It should be minus for positive, so it should be negative 2t. And then cosine square root of 2t. Because this is beta squared, so beta is square root of 2. And then plus this is square root of 2 over 3. And then Laplace inverse for the shifted one is e negative 2t sine square root of 2t. Well, I think you can just write the same thing as this, but I just make 2 over square root of 2 becomes square root of 2. Okay. So this is the answer. So, okay, let me just recap. This e with power something here with power of t is our translation, our shifted s. Okay. The right one is just our function, f of t, right? F of t. So we say that we are shifted from s to s minus a being this minus 2. Okay. So two different approach. The first one through some partial fractions, okay, as usual, and the second one is completed square. Okay, completed square. So the idea behind the completed square is to make the top equation and the bottom equation having the same structure or the same component. Okay. So when you complete the square, you have, for example, s minus 3 squared, or s minus 3 and then with bracket squared. Then you need to have the same component in the top equation. Okay, you need to force out this s minus 3 out. Okay. Okay, any questions? Okay. Questions? So far, is it okay? Is it confusing for you, or what do you think? Confusing. Okay, okay. All right. So basically, the Laplace. So the idea of Laplace is actually you use Laplace to transform your functions, right? But actually, Laplace, uh, why we need Laplace is, yeah, Laplace is hard because uh, you need to have some sort of transformation of your some basic functions, right? And then you are going to inverse the inverse inverse those Laplace, right? So basically, because Laplace is needed to solve some differential equations, because you see that when you have differential equation and maybe it's making uh, more and more complicated one. Why Laplace is making easier is because Laplace can make those differential become algebraic equations, become a polynomial. And when we have a polynomial, it becomes easy to rearrange. That's what Laplace is. Okay? So why they are using Laplace more and more, because they can rearrange some sort of equations easily in terms of Laplace, okay, when we transform it. And then aside from the original Laplace and its inverse, we may also have, if we shifted our or if we translate our transform function. And when we translate, which means that we are going to multiply the original function with some exponential, okay, with some exponential with power of constant t. The constant becomes our shifted graph in the f of s. So maybe let's recap a little bit. So here is a graph of capital F with variable s, right? So when we have when we shifted the f of x to f s minus a, it means that this is the Laplace of e with power of a t multiplied with f of t. So if you have original f of t, when we are immediately when we think on shifted, then that means that we are going to shift through this constant a. Okay, so we are going to shift it to s minus a. Okay, and when we deal with this, then we can transform inversely, okay, inversely from the s to t. Okay, so that's the thing. So if we transform like this, we know that we can write with s minus 5. And if we revert, we can also refer. So when we revert this, we can refer that this is basically saying that we are having some 6 over s with power of 4, and we are going to revert this uh, taking the inverse, and this is taking the s to s minus 5. So we are having s with power of 4, what kind of functions this is. And then we remember that this is actually, we remember this is a t with power of 3, and this minus 5 becomes e5t. Okay, we remember that as well. Okay, so I think uh, to help you overcome some challenge and problems in Laplace is, I think, to have more and more practice and familiarity with the Laplace. Okay. The basic table you have that I give you, I think, in the Laplace introduction, and its inverse is practically the most used in this chapter. Okay. So I hope you are able to familiarize with the at least the basic table, right? The basic table. Okay. I think I will just give you some sort of, I think, 2 examples or 3 examples, and then we can finish for now. And then the next session, the afternoon class, we are going to continue with a more I'm not say it's difficult, but it's a little bit abstract, because you will learn that there is some kind of derivative and integration that is uh, not easy to visualize, not easy to draw, and not easy to imagine. Okay. Okay, let me give you another example. So solve with Laplace y double prime equal to t squared e 3t. Okay. Now if we are doing Laplace, so Laplace of y double prime, 6 Laplace with y prime plus 9 Laplace of y, and Laplace Laplace of t squared, or let me write e first so you can immediately connect with the previous structure. Okay. Let me start from the right. This is because we have the e, that probably this will be the translations, right? So let me just go to the t squared. T squared Laplace, this will be 2 over s cubed, right? But we need to translate from s to s minus 3. So we can write this 2, well, it's 2 factorial, but it's 2 factorial, it's 2. So 2 over s minus 3 cubed. Okay. Okay, now we are going to solve this. Oh, let me give you the initial condition. I forgot. Y0 is 2, y prime 0 is 17. Okay. Okay, the double prime here, this will be s squared, capital Y s, minus s, y0 minus y prime 0, okay, minus 6, y prime become s, sys, and minus y0, and then plus 9 ys. Okay. Okay. As usual, we start by grouping the ys. So s squared minus 6s plus 9. And we can write this is 2s, this is 17, this is 17. Okay, and then we can set up so this will be 2s. So let me write 2s. Oh, sorry, this is 2. So minus 2 minus 6 plus 12 minus 17 is minus 5. So going to the right is plus 5. Then plus 2 over s minus 3 cubed. This part here is s minus 3 squared, right? So we can say that we can divide all with s minus 3 squared. So 2s plus 5 divided by s minus 3 squared plus 2 divided by s minus 3 cube plus 2 is 5. Okay. Yeah. Okay. I think this part here, the first part, if you remember that this is actually the first part here, the same thing, right? Same thing here. So we can rewrite this. Okay, rewrite, and we can decompose through with 2 and 11 as a constant. So 2 over s minus 3 plus 11 s minus 3 squared, and then plus 2 s minus 3 with power of 5. Okay, this is our capital YS. Now, we take the Laplace inverse of the y of s to make the solutions. Okay, so 2 Laplace inverse of 2 over, sorry, should be 1. So 1 over s minus 3 plus 11 Laplace inverse of 1 over s minus 3 squared, and plus 2 Laplace inverse. Now remember, if we have this with 5, okay, if you want to convert back, the easiest way we are going to do this is we are going to have 4 factorial here, right? If you want to convert back. So we need to divide this with 4 factorial. Okay. Okay, I hope you get my point here. Because we are going to transform, remember that we have 1 factorial s squared, right? If you want 2 factorial s cubed, it's easier to convert, right? So we are going to convert this 4 factorial. Okay, so this part here, this will be, or maybe this part here, this is equal to 1 over s squared when s goes to s minus 3, right? Or we can call that this is just t, right? T, and then the shifted is e 3t. Okay. Now this part here, same thing. This is Laplace inverse of 4 factorial of s with power of 5, which we are going to shift this s to s minus 3, or we can have t with power of 4 and then e with power of 3t. Okay, so all in all, this will be 2e3t plus 11t e3t plus 2 over 4 factorial. 4 factorial is 24, so this is 1 over 12. T with power of 4 e3t. And this will be our solution. Okay. So using Laplace is making the solution is more exact and precise. Okay. It's helped us actually to solve most of differential equation, the linear one, and gave us the very precise, exact solution, right? Instead of just if we remember some of differential equations method, they requires to looking the homogeneous part, looking the non-homogeneous part. But using Laplace, we can transform and then invert back and then writing the exact solution of the equation. We don't really care much about homogeneous and non-homogeneous anymore, right? Okay, I think example again. Okay, another example. Let's solve y double prime plus 4y prime plus 6y equal 1 plus e with power of negative 3. The initial condition is y0 is 0 and y prime 0 is 0. Okay, if you want to try, we can try this. Yeah, we can try this for a while. And you will notice that there will be some sort of fractions that is similar to what we have before, so that we can just use the same conclusion. So first thing, doing Laplace, okay, use the initial conditions, solve the Laplace form, solve for capital Y or capital any variable you have, okay, and then transform back using inverse Laplace. That is practically what you're going to do in all Laplace transform. Okay. Do Laplace, rearrange, doing maybe partial fraction or something, and then goes back to the original one. Use inverse Laplace. Okay. So Laplace, rearrange, inverse Laplace, find the solution. Okay. So it's always like that. Oh, anyway, do you learn Laplace before? I think it, it's 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 it, it's I mean, in your previous lecture with engineering math, maybe with different professor, you also learned Laplace, right? But do you learn until the Dirac delta, the Heaviside function? I think still, right? You learn that, right? Because uh, that is one of important function in engineering, the Dirac delta function, or the Heaviside, the unit step function. We are going to learn that, I think, in the afternoon class. Okay, but let me just go for example here. Okay, doing Laplace. First is Laplace. So Laplace. So Laplace of y double prime plus 4 Laplace of y prime okay. This will be s squared capital Y s plus, right, s, and then plus y prime 0 plus 4 Laplace y prime is s ys minus y0, and then plus 6 ys. And then we can directly write this as 1 over s for 1, and then plus 1 over s minus minus 1, so s plus 1. Okay, we can factor out the s squared plus 4s plus 6. Okay. And then we are having the 0, 0, and 0. Yeah, all 0. And we have, if we combine this, s plus 1. So s plus 1 plus s, so 2s plus 1, okay, over there. And our capital Y becomes s plus 1, s squared plus 4s plus 6. Okay. Now we have, if we separate this 2s, divide by s and s plus 1, and then plus, this become s squared plus 4s plus 6. Or probably we are having directly partial fractions, I think. Let me just write over s plus f plus 1 plus s squared plus 4s plus 6. And we can take this a, b, cs plus d. Okay. Okay, solve one by one. Plus bs, and then plus cs plus d, s squared plus s. And it should be equal to 2s plus 1. Okay. Okay, we take so this will be and this will be cs plus d, so cs cubed plus ds squared plus cs cubed, cs squared, sorry, cs squared plus ds. So as cubed plus 5as squared plus 10as plus 6a plus cs cubed plus ds squared plus cs squared plus ds. Okay, it's quite long, right? So we can write a plus b plus c. 5a, okay, 5a plus 4b plus d plus c, or plus c plus d, plus 10a plus 6b plus d. Okay, 6a plus 6a. So a is 1 over 6, right? And a plus b plus c is 0. So b plus c is negative 1 over 6. 5a plus b plus c plus d. This is also 0. And 10a plus 6b plus d is going to be 2. All right, b. So 5 over 6 plus 4b plus c plus d is equal to 0. Okay, I think we can solve this. C is, so we can have 3b plus d is 4 over 6, negative 4 over 6. Okay. 3b plus d. So d is negative 4, 6, negative 3b. Okay, this is 3b is 1, so b is 1 over 3. Okay. And the rest is, I think, just 0. So a is 1 over 6, b is 1 over 3. Okay. Oh, c, you can say c. So 1 over 3 plus c is negative 1 over 6. So c is negative 2 over 6. It's negative half. And d is negative 4 over 6, negative 3 over 3. So this will be 6 over 6, or this is negative 5 over 3. Okay, we input into our solution. Okay, let me write into a new page. That is, let me write a over s plus b over s plus 1 plus cs plus d divided by s squared plus 4s plus 6. So a is, from our calculation, is 1 over 6. B is 1 over 3. C is negative 1 over 2, right? And D is negative 1 over 3. 5 over 3, sorry. So 1 over 6 over s plus 1 over 3 over s plus 1. This is negative half, so I will write negative outside to make it clear. So 1 over 2s, or s over 2, plus 5 over 3, and then over s squared plus 4s plus 6. This is precisely what we have in, wait a minute, where is it? Oh, here. This one. The same, right? So we can take the inverse now. So 1 over 6. So this is going to be y over t. 1 over 6 Laplace inverse of 1 over s plus 1 over 3 Laplace inverse of 1 over s plus 1. Okay. And because we already have our solutions from previous case, then we can simply take this Laplace inverse of, this is s plus 2, s plus 2 squared. I will skip some part here because we already done this before. And then negative 2 over 3 square root of 2 Laplace inverse of square root of 2 and s plus 2 squared plus 2. Okay. This is 1 over 6 plus 1 over 3e negative t negative half e negative 2t for the translations, and cosine square root of 2t. And negative square root 2 over 3, this is sine square root of 2t. Oh, the e, forget the e. Okay, here it is, the solutions. Well, it seems a little bit difficult, right? Not I think not difficult, but it's complicated. If you are taking it slowly, I think you will gonna make it. Okay. Okay, any questions? If not, we are going to have, as usual, we are going to have our feedback. Okay, is there any question first? Okay, if not, then I will move to our feedback, and please, as usual, join our feedback. Okay, any questions? If not, then I will move to the feedback time. Okay, okay, let's stop sharing. Okay, so can you see my screen now? Okay, let's go for some feedback session. I think I forgot I prepared two, I think three questions. Three short questions. And don't worry about the Laplace transformations, the basic table. You can always just looking at your table and write your Laplace directly. Okay, are we ready now? Please scan the QR code or go to the website using this code. Okay, I think we can start. Okay. Okay. Okay, wait. Okay, wait a minute. What? Wait. Okay. 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 You use your student ID. Okay. Okay, 3, 2, 1. Let's start. Okay. Okay. Remember transformation, Laplace transformation, and its inverse is linear. Okay. Okay, don't forget to use your student ID. Okay, use your student ID. If not, then I cannot arrange in your grade. Okay. Question 2. Okay, true or false? Yeah, you have 1 minute to check. You can check your notes what your cosine and sine should be, or if it's true, then it's true. If it's false, then what it's wrong. Okay. Okay, 5, 4, 3. Okay. It should be false. It should be false. Okay, it should be false. Okay, who is Watson? Watson. Okay, can you check? Can you change your student ID to your student ID? Okay, last question. Get ready. Oh, okay, Watson. Time. So A plus B plus C plus D. Okay, I'm giving you around 1 minute 40 seconds. I hope it's easy to write, but careful. Okay, careful. It seems plus plus. Careful on the sign. Careful on the sign. Okay. 15, 14. Okay. 12, 11, 8, 7, 6, 3, 2, 1. Okay. Yeah. Okay. Good. It's 15. Okay. So careful on the sign. Okay. Who is the winner? Okay. Okay. So congratulations. Okay. So before we end, I want to have more feedbacks on our quiz. Okay. So please adjust the scale if you strongly agree or disagree with all the statements. Okay. I just want to know about our quiz, and then it will be my consideration for the next exam. Okay. Whether the time is too short or maybe some questions are too difficult to understand. Maybe the English part you don't really understand the sentence. Okay. Okay, please fill in. And I still have one more in the last page for your student ID. Okay. Now last part is just give me your student ID, and if you have more feedbacks, maybe you want to write regarding to your quiz, okay, or maybe the lecture so far. Especially now we are in Laplace. Okay. If not, then okay. Okay, longer quiz time. Okay. Yeah, I think. Okay, if there is no other feedbacks or questions, uh, I will stop until here and see you in the next session, in the afternoon session. Okay. So thank you for joining, and I will stop the sharing screen. Yeah, you're welcome. Okay. Okay, see you. Okay, stop this. And